Hi, everybody. My name is Dan Harris. I'm from ABC News. I'm one of the reporters and anchors over there. I am actually the anchor of the weekend edition of Good Morning America, which means I have to be up at 4 o'clock tomorrow morning. So as a payback, I expect all of you to watch our broadcast, which airs at 8 o'clock on Channel 7. I've been feeling smug recently about this whole issue of long-term memory because just the other day I remembered my second anniversary with my wife. She told me that I was not allowed to gloat because I had actually, on the day of our wedding, put an annual reminder in my BlackBerry. She further reminded me that I am disqualified from gloating about any area of long-term memory since, as an anchorman, I'm incapable of saying anything beyond 2 sentences without a teleprompter present. Tonight we are going to talk about long-term memory. Play a mind game with me if you don't mind. Try to recall, if you can, your earliest memory. Or if you can't get that, try to recall a family vacation or the most embarrassing thing that happened to you as a kid. And as you're conjuring these images, consider how amazing it is that there may be decades between the event and the present moment, and yet for many of us, these memories are incredibly vivid. So tonight we have an incredible panel, and we're going to get into how reliable these memories are, in some cases less than you might think. If you have a spouse, you already know this. And we're going to get into, my wife's not even here, she's going to kill me if she finds out I said these things. We're going to get into the questions of whether memories are changed, sanded down, enhanced in any way by time, and also emotion, which is particularly interesting. As I said, we've got a really interesting panel, so I'm going to take a seat and introduce them one by one and let them come in and take a seat. We're going to start with a man named Daniel Schachter. Cue the music. Sorry, the music's a little eerie. You don't deserve that. Daniel is a professor in the Department of Psychology at Harvard University. His research explores the nature of memory distortions, how individuals use memory to imagine the future, and the effects of aging on memory. He is known for his book, The 7 Sins of Memory, about different ways memories can go awry. Our next panelist is Todd Sachter, who's a professor of physiology, pharmacology, and neurology at SUNY Downstate. Hey, Todd. In 2002, it was Todd's lab that demonstrated that the molecule PKM-zeta, am I pronouncing that correctly? Yeah. All right. It's the last time I will do that tonight, was both necessary and sufficient for maintaining long-term memory. His research was considered one of the breakthroughs of the year by Science magazine. Our next panelist is Elizabeth Phelps. She is a professor of psychology and neuroscience at New York University. Elizabeth's lab has earned widespread acclaim for its groundbreaking research on how the human brain processes emotion, particularly as it relates to learning, memory, and decision-making. And finally, Lynn Nadel. Lynn is a professor of psychology and cognitive science at the University of Arizona. From Arizona, when you didn't wear a bolo tie tonight.
Born and bred in New York.
I see. Well, then you're excused. His research is focused on the functions of the hippocampus in memory and spatial cognition and has led to significant contributions in new theories of memory, including re-consolidation, which we're going to explain, and the cognitive map theory of the hippocampus. So, thank you all. I think, Lynn, the idea is to pick on you first, and not just about the lack of a bolo tie. We want to ask you first to set the parameters from a definitional standpoint tonight. How do we define memory, and how does one get one?
We define memory as some sort of a record of prior experience. Something happens, and the brain encodes that information, and then subsequently we retrieve it, and that's what we call memory. But there's a lot of processes that go on between encoding and retrieval, something we call memory consolidation, and most of the research you're going to hear about is about those various stages of memory. But perhaps one of the most important facts we know about memory now is that there isn't just one kind, that there's multiple kinds of memory, and that they differ from each other in their properties and in the underlying brain substrates. So that's a crucial fact that influences a lot about what we now research with regard to memory.
which, thank you very much, tees up a little video that we happen to have on hand, which explains this issue of the many types of memory we have. Let's check out this video.
Your memory is kind of like the storage unit of your life. Stuffed inside your life's dresser are different types of memory. Let's look at 4. In one drawer, you'll find your episodic memory, which records events in your life, like your favorite childhood birthday party, your prom, or even what you ate for dinner last night. Then there's your semantic memory, which is key to remembering facts. It's the memory that helps you win trivia games. What year was our country founded? Your semantic memory tells you 1776. After playing the trivia game, you go bet on a lottery ticket. The numbers 1776 might just magically pop into your head. Priming is the unconscious activation of a thought or memory that can then pop into your mind. Hidden in the drawers are conditioning memories. These recollections cause us to respond to a stimulus in a certain way. Remember Pavlov's dog? The dog was conditioned to salivate every time a bell rang. Conditioning, priming, semantic, and episodic. All are different types of memories that work together to store our history and make us who we are.
So Dan, that went by pretty quick. Can you break it down a little bit?
I wouldn't teach it that way, but it was a fun video. As Lynn pointed out, one of the fundamental lessons really of the past couple of decades of memory research is that even though it's easy to talk about memory as if it were a single thing, some sort of persistence of the past into the present, there are these multiple forms of memory, some of which we just saw. And one of the important ways that we've learned about these distinctions has been through the study of some very interesting people who unfortunately have had a certain kind of brain damage that has caused a severe memory deficit. And this brain damage typically involves a structure we already heard referred to briefly in the introduction, the hippocampus. It's in the inner part of our temporal lobe, and we learned about the importance of the hippocampus and some other structures nearby in memory, probably most famously from the study of an amnesic patient that some of you may have heard of. He was known in the literature by the initials HM. And way back in the 1950s, HM was a young man who had surgery because he had a problem with epilepsy that was probably going to take away his ability to speak. And people didn't know at that time that the hippocampus was important for memory, so it was removed on both sides, left and right, from HM. And what people immediately noticed is that while on the one hand, he seemed like the same person from before the surgery, he could still use language, perceive the world, carry on a conversation, he had utterly no ability to remember what had just happened. If you spoke with him for a couple of minutes, you might think he was a jovial, friendly person, but then if you walked out of the room and came back in, he would have no idea who you were, even though he seemed otherwise normal.
Was he aware that he couldn't remember?
He became aware. It's a very interesting question about these kinds of amnesic patients, is whether they are aware. Some of them are. Others who have damage to other parts of the brain, particularly up in the frontal lobes, which are very much involved in judgment and monitoring, tend to be totally unaware of their deficit. But he had some mild awareness. Well, if you fast forward a couple of decades, what was learned is that even though it seemed that HM had totally lost his ability to form new memories, he hadn't. He and other amnesic patients like them could form some kind of new memories in a totally normal manner. They just weren't memories that could be consciously called up to mind and re-experienced as a memory. So what he had most fundamentally lost was episodic memory, which we heard defined as the ability to kind of recollect your personal experiences. You can all easily remember what you were doing a couple of hours ago before you came to this event. Well, a patient like HM couldn't. But there are other ways in which patients like that can show that they retain their experience. And one of those shown in the video is called priming. That's a phenomenon I've been really interested in over the years, because what we learned is that patients like HM and other amnesic patients can show a totally normal priming effect. That is, for example, if you show them a picture of a familiar object, and then later on really flash that object like an elephant or a table, you really flash it very briefly so you can barely see it. and it's hard to identify, so that if you've just seen it in full view a few minutes earlier, it becomes much easier to identify for people like us. That's called priming. You're primed so that you can perceive that degraded stimulus. Well, HM and other amnesic patients can show that priming effect to the same extent that anybody else can, but they don't remember consciously having been exposed to the stimulus. So that's one very dramatic example of how different kinds of memory can be pulled apart. And there's been some really interesting recent work with priming just in healthy individuals, a kind of ingenious experiment that had been done back in the 1980s using this technique of showing people pictures of objects and then asking them to identify the object from a really quick exposure where it's very hard to see without priming. And the researcher had found a priming effect, reported it 20 years ago in the literature, and then he did something very interesting. He followed up on his subjects who had been college students at the time. 17 years later, he somehow tracked them down in the phone book. He brought them back into the lab, and lo and behold, he still found that they showed a priming effect, even though most of them didn't even remember that they were in the experiment, let alone having seen any pictures of the objects for which they were primed. So priming is really a different kind of memory than episodic memory. It doesn't rely on the hippocampus, it's non-conscious, and provides a very dramatic a difference. Somatic memory is also different from episodic. The example in the video, for example, recalling facts, general knowledge, who is the first president of the United States. And we know that there are other kinds of patients who have problems with semantic memory. They can't pull up those kinds of facts. They don't understand concepts, and yet they have a normal episodic memory, kind of like the reverse of HM. So that's another way that we've learned that these different kinds of memory are different. And more recently, studies using brain imaging techniques where you can scan people while they're learning and remembering. You put them in a scanner and measure changes in the brain that you can accurately localize to within just a few millimeters of where they're occurring, show nicely that these different kinds of memories activate or are associated with the activation of different regions in the brain. And then finally, conditioning was also mentioned in that video, and one of our panelists, Liz Phelps, has done some very interesting work also with patient populations that she would like to tell you about on conditioning.
So Pavlov described conditioning as the simple association between a bell and food, which led now for the bell to generate salivation. So the dog was preparing for the food. And this is just learning through simple association. The dog does nothing. He's just experienced the events that are around him and learns this association, and now it changes his physiology. One of the types of conditioning that we study a lot these days, because it has implications for things like anxiety disorders, is the conditioning of our emotional responses, our fear response, when our heart rate increases, when we sweat. So for instance, if you had an argument with a friend and it was very heated, the next time you see that friend, it may be the case, you probably would remember that the argument occurred, but you also may get tense and feel uncomfortable because you now have associated that friend with this physiological response that indicates some level of anxiety or fear. And this type of conditioning depends on a separate brain region called the amygdala, which is quite a small region, about the size of your thumb tip, but it's very important in the generation of fear. And again, it's independent from the hippocampus, so patients with damage to the hippocampus will be able to learn to fear a blue square paired with shock, although they could never tell you that the blue square was paired with the shock before. And what's particularly interesting about this type of memory that makes it somewhat different than the ability to recollect information is that we think those simple associative memories that are linked to your fear response are actually stored in the amygdala itself. So that presents an opportunity perhaps to target those memories when we want to, say, treat disorders.
And we were going to talk to you, Todd, about the importance of your lab's discovery in all of this.
Oh, okay.
Can you...
Well, basically, in the definition that Lynn mentioned, in which a memory is stored as a record of an experience in the brain. So to me, the fundamental question is, what is the nature of that record? I mean, what is the biological basis of memory storage? And the thing to realize is that no one's had any idea at all. I mean, it goes back to Plato writing about writing on wax tablets as the metaphor for memory. And so 100 years ago, when scientists discovered by looking at microscopes that there are neurons and that there are connections between the neurons called synapses, people speculated that the changes in the strength of those connections would be involved in the mechanism of the memory. But no one had any idea what the persistence of mechanism was. So just to give an example, a year from now, people in the audience may have a connection between Maurice Chevalier and Danny Kaye, the comedian, because this is his theater, and 5 people sitting on these cool red chairs. And so the memory, so they may know Maurice Chevalier, and that was probably, if they're thinking that, that's probably maybe 1,000 to 10,000 neurons firing at once in a network. And that network had never been connected with Danny Kaye. And that network had never been connected with 5 people talking about memory for an hour and a half. But a year from now, the people in the audience might remember that. And that's because some change happened in that synaptic connections. And so basically that was the big discovery that my lab and my collaborators made almost precisely 5 years ago, which was we discovered the first molecular mechanism for that memory storage. And what was shocking to pretty much the entire neuroscience community was that it was a very specific molecule. And the nature of this molecule was an enzyme. So hardly anyone expected that. And what an enzyme is basically, it's a type of protein that catalyzes, that helps, that promotes a chemical reaction. So what we found was that in the brain, when a connection between Maurice Chevalier and Danny Kaye has been made, those synapses that were already there now started making this molecule, which is called protein kinase M zeta, or PKM zeta, that was persistently doing a chemical reaction. So that was our hypothesis. So we tested that hypothesis by giving to an animal, experimental animal, a rat, into their hippocampus, the part of the brain that's storing for animals, non-human animals, storing spatial information. And we can talk about that later on. So we basically taught an animal to avoid an area of space, and then waited a day, and then injected into the hippocampus of the animal this drug, which is called ZIP, for zeta inhibitory peptide. We injected this drug ZIP, and for the first time anyone has ever shown, we're able to erase that memory.
So we have video of this, right?
We have video, yep.
Should we show it now, you think, or you want to hold it?
Sure, so let me just explain what they're about to see. So the experiment was, it was a task created by Andre Fenton, who's a colleague at Downstate now at NYU. And basically we put a rat into this carousel that's slowly rotating. It's around this diameter. And it slowly rotates. And the carousel is in a room, right from you to you. And on the walls of the room are various objects, clocks and doors and things like that. So the animal is put onto this carousel, and it's slowly rotating. And it's rotating into, when we're training the animal, a shock zone. So it's a little pizza wedge-shaped sector. And so the animal learns to avoid that shock. So looking down now with a camera, let's see the film. So this is a naive animal, and we put the rat into the apparatus. That's a little LED light, that's just so we can see it. Now the shock is not on. See, that's the gray zone, that little pizza wedge. That's where the shock will be in a few minutes. So right now we put a naive animal in. It's spending most of its time on the outside of the apparatus, maybe looking through the walls, which are clear plastic. Now we turn the shock on for 10 minutes, and we turn it off for 10 minutes, put it in its home cage. And after 8 of these 10-minute episodes, the animal has learned to avoid the shock zone. So notice that the information that's on the floor of the apparatus is useless. The rat has to look out into the room, and that really engages the hippocampus. So now a day later, we put the rat back in, and we inject salt water, saline, as a control. And we're testing with the shock off.
These injections are into the hippocampus, right?
Yes, hippocampus on both sides. So you see the rat avoids. Shock is off, but it just avoided that area. Now we take another set of rats, trained them exactly the same way, waited a day, and injected zip. No evidence of the memory having been there. In fact, if you take a picture of exactly the same rat when it was in its naive state before it was trained, and after its memory had been erased, there's absolutely no difference in its behavior. So we can turn that off.
So is this scalable to humans in any way, or does this have clinical applications that we would care about?
Yes.
Could I erase my wife's memory of various... Never mind, carry on.
Well, right now, it would erase all information, we think, in your wife's brain.
Right. Can I have a minute to think about that?
No, we didn't call it Stepford drug or anything like that. But, so the goal eventually is to understand how this molecule is storing memory and understanding it in real detail so that we can harness the power of this ability to erase the memory. So let me just say, people have gone out since these 5 years, many of the different types, in fact, all of the different types, except for priming, all of the different types of memories, from Pavlovian conditioning to spatial memories to fear conditioning, they've all been erased by this drug, and now 3 other different versions of different ways of inhibiting PKM-zeta. So the evidence is pretty strong that this is a fundamental mechanism for the storage of memory in the brain. So to answer your question about clinical, this is a discussion here about memory, but the brain doesn't know that. The brain is using information storage for all sorts of things that we're not even calling memory. So for example, there's a disease called chronic neuropathic pain, which is essentially the memory of a painful incident that's happened that's set up in the spinal cord and in some unconscious areas of the brain. And other researchers, not from my lab, have used ZIP to erase those memories in rats, in rat models of chronic neuropathic pain. So I think that's the first clinical application. And late in the last few months, we've shown we can actually enhance old memories by putting more PKM-zeta in, but again, using a virus. So we probably can't do that in people. But the goal of getting specific memory erasing would be to harness the potency of PKM-zeta and its inhibition, and that process of re-consolidation that you mentioned. So, but before we do, there's one more thing that I want to show, if I could. Basically, by identifying the molecule that's essential for storage, we can now actually see a memory being stored in the brain. So if I can just show that, what we call the rainbow slide. So basically, this was that saline-controlled animal. We're looking at PKM-zeta. The more yellow and the more red it is, the more PKM-zeta is in in the brain. So this is that hippocampus little structure that we talked about. So that's an animal that was naive and not trained. And here's an animal a day after its training. And all that yellow dots in there are the PKM zeta molecules that have been formed and maintained for a day. Scientists have actually gone out to at least a month, and we see that increase. And in that my last slide, we can now look at real detail. This is a neuron that we've injected with a dye, and we could see that's the cell body, and that's the dendrites, and these are the synaptic connections are on these little mushroom-like things coming off of the dendritic shaft, and these are called spines. So we can actually, for the first time, say how many synapses are actually involved in the encoding of a memory. Here we see one right here, it's yellow, here, there. These other spines don't have PKM zeta. So we're actually counting the synapses in order to say how many synapses are actually storing a long-term memory. No one had any idea or any way of doing something like that.
I apologize because I kind of didn't quite fully, and I hope I'm not alone on this, but I didn't quite fully understand the clinical applications here. This obviously has not been tested in human beings, but what do we think would happen if we gave zip to a human being? That would wipe out all of their memories, but not their ability to remember going forward.
Right. The thing about zip is if you give it to an animal, it's most likely probably, I don't know, since most forms of long-term memory have been erased, I would say most of our conscious memories would certainly be erased. There will be a basic instinctual behavior that we as Homo sapiens have inherited in our DNA, and that allows us to walk, probably, that our circuits in our brain and spinal cord are allowing us to walk, to chew food, to eat. All those things would probably be preserved. They may be a little clumsy at first, but they'll be preserved. But then you could train someone all over again, because the key thing is this drug zip doesn't destroy the brain, it just erases the information, like wiping a hard disk.
Restoring it to factory settings.
Restoring it exactly to the factory.
So it's like the Bourne Identity in some ways, right? I mean, isn't that what happened to Matt Damon in the Bourne Identity? They failed, but they tried to erase his memory because they'd sent him on some sensitive mission, right? I mean,
he was still pretty good at karate. See, that would have been gone too, right? And he had all these non-conscious skills that allowed him to, figure out eventually. It's closer to, say, Men in Black.
1, 2, 3, or 4.
Yeah.
The first one was the best. So,
we can have that debate later.
Yeah.
There's no debate on that.
How do you feel about the lethal weapons?
So the thing about Men in Black, that's an alien technology, and we don't understand how that works. So they had much better control over the timing. Like I say, right now, the zip will just erases all memory.
So has the Pentagon called you? Because I feel like this would be useful, weaponized.
Not that I can recall.
Okay. I feel like he's used that joke before.
I was waiting for this day. I've never used it before.
So I'm sorry, I'm torturing you at length here because this is really interesting. But the other question I would imagine that's at play here is whether we can attack specific memories as opposed to restoring to factory settings, getting rid of one application on our
Right.
iPod.
I think we have to know, and the audience has to know more about this process of reconsolidation. So maybe we should talk about that.
You're doing a good job of leading us to the next thing here, reconsolidation.
So Todd was talking about a way that all memories are held together. So that's why when you give zip, you erase all memories. If we want to target specific memories, a technique that we're using now that's really been studied quite a bit over the last decade. It was an old idea, but it got sort of renewed about a decade ago, is this notion of reconsolidation. So I'm going to walk you through this, this little graph here. So we used to think, no, it's okay, I'll just talk. We used to think, if you look at the top line here, that when you learned something, we knew there was a period of time that it took for the memories to become stored in the brain, for the synaptic processes to occur that are that memory. However, we thought that now when you retrieve that memory, you retrieve the original memory, but then if you retrieve the memory again, you once again retrieve that original memory. So once the memory went through this process of consolidation, which takes time, and before the memory is fully consolidated, it's fragile. You can disrupt it. So if you know somebody who had a concussion and didn't remember what happened right before, it's thought to be due to the fact that the memory storage process was disrupted. But once the memory is stored and it's consolidated, it was thought to be there in your brain until something like zip came along. And every time you pulled the memory out, it was like pulling it out of a file cabinet. You bring the memory up, you put it back. Next time you want to get that memory, you bring it up, you put it back. This was the classic view of memory. And about a decade ago, there was a paper by Kareem Nader, who was working at NYU at the time. And he renewed interest in this second idea of memory, and it's called the reconsolidation view. And if you look at the bottom line here, the reconsolidation view suggests that when you learn something, there's a period of time that must occur for the memory to be consolidated, for the storage processes to occur, to lay the memory down in your brain. And now, however, if you retrieve the memory, it has to go through a second storage process. And this second storage process we call reconsolidation. And what this does is it gives you a second opportunity now to disrupt a memory. So if a memory, when you retrieve it, has to be stored again, it's fragile once again, that specific memory. And what Kareem showed about a decade ago, he used rats, and he looked at this type of memory we call fear conditioning. So he took rats, he gave them a tone, he paired a shock with the tone. So now the rats, when they heard the tone, were afraid. He let that memory consolidate. He waited a day, he also waited a couple weeks. He brought the rats back to the lab. He then had them, he played the tone just to reactivate that memory. And he then injected a drug into the amygdala, where we know this site of memory storage is for these types of simple fear memories, that prevents protein synthesis. Protein synthesis is needed for the storage processes of memory. And then when he tested the rats later, a day later, they showed no evidence of the fear. So he played the tone, they walked around, there was no evidence they were afraid of the tone in that case. So what he was able to do, now this didn't happen if he didn't play the rat that tone. So just injecting the drug into the amygdala did not disrupt the fear memory. You had to play the rat the tone and then inject the drug, because you had to have the drug on board while the memory was being restored or reconsolidated. So this type of mechanism is a potential mechanism to target very specific memories for disruption, because you have to retrieve the memory and have that sort of on board when you interject now and do something to disrupt that memory. Now the problem in this type of experiment that Kareem did in rats is that you can't, if you wanted to take it to humans, particularly with fear memory, and there's interest in this because of the importance of the fear response and things like PTSD, is that you can't inject these protein synthesis inhibitors into the amygdala of people. Wouldn't be safe. So what we've done recently in my lab is take another view of how you might interrupt reconsolidation of a specific fear memory. So if we think about why we have reconsolidation, why would it be the case that every time you retrieve a memory, you have to restore that memory? One theory is that this allows us to update the memory when we retrieve it with new information that may be available at that time. So now when you restore the memory, it's not the original memory as it was when you first learned it, it's the original memory plus new information available. And this just tells us that memory, it's a mechanism for memory to be dynamic. so that memories can change over time. Whatever led you to retrieve a memory is very likely useful in the future as well. So now those things are stored together. So if this is the case, we should be able to use re-consolidation and what we know about how it works and the timing of it from research in rodents and disrupt very specific fear memories in humans by introducing new information while the memory is being reconsolidated or restored. And that's exactly what we did with fear memories in humans. Just like in rats, we taught humans to fear a blue square by pairing it with a mild shock to the wrist. We then waited for that memory to get to consolidate. We brought the subjects back a day later, and these were just, when I say subjects, I mean NYU undergraduates.
Normal subjects.
Yes, normal subjects. We brought them back a day later. We showed the blue square, and then, while the memory was being restored, we presented the blue square a number of times without shock, so they now learned the blue square was safe. And what we found, if we did that during the time window when the reconsolidation process was occurring, they no longer showed evidence of the fear of blue square later on. If we did that type of learning at another time, the fear memory would come back. So learning that the thing is safe doesn't really disrupt the original memory unless you do it when the memory is being restored. And so we're starting to be able to use these techniques and also looking at drugs that we know might be safe in humans to see, can we disrupt very specific memories by having those memories on board while we now engage in what we have to do to change the memory. And this is not just happening, we think, with fear memories, although they get disrupted because it's a very simple memory that's stored in a localized area of the brain, but it also happens with your ability to recollect information. And Lynn Nadell's been doing research on that.
Can I just ask you a quick question?
Sure.
If every time we recall something, it is in play for being changed, how can we trust anything we remember?
So it's not that, it's not that now the original memory is completely erased. If I injected a drug, you could argue that I'm actually erasing the original memory. It's actually incorporating this new information. So when it comes to a fear memory, right, incorporating information that the thing you feared was safe, right, now changes your fear response. Okay, so that is now significantly changing your fear response. But I could actually, you could retrieve the fear memory and I could do nothing. What we think that actually does is it makes the memory stronger. So it's been argued, for instance, in schools, if you test frequently, that you will show better memory over time. And it's been argued that one of the reasons this might occur is because every time you retrieve something in a test, you have to restore the memory. And this, by restoring the original memory multiple times without introducing a lot of interference, which we specifically did in our experiment, what it actually does is creates a stronger memory. You've now stored the memory once, you've stored it again, you've stored it again, you've stored it again. So it's thought to be perhaps a mechanism underlying effects in education that enhance knowledge with frequent testing. So it really depends on the type of memory. It depends on the type of disruption you're doing, whether or not you're going to end up having a completely different memory or a memory that's got little components of both things that occurred. In the case of a fear memory, it's a very simple association. And what we were able to do by taking advantage of the timing of this process is essentially rewrite what the meaning of that stimulus is to you, right? What the value of that stimulus is to you, so that the fear never seems to return. But with other types of memory, this process has a different outcome. So Lynn can talk about that.
So we started from the same premise that memories were subject to this updating process, but we wanted to look at it in a framework that was different than fear memory, something a little bit more typical. So an example I like to use is that when you sort of go away for a few days and then you come home and your wife has rearranged the furniture in the living room and you walk in, you actually, the next time you want to be able to remember where the furniture is now. You want to update your memory of the layout of the furniture compared to the way it used to be. So we assumed that this process of memory reconsolidation wasn't just some quirk of the system that would allow you to disrupt memories, but it was in fact a natural process by which you could update your memories so that they would be more accurate going forward. So we designed an experiment that ran sort of like this. We brought subjects, again, the typical subjects, college undergraduates. It's not clear how typical they are, by the way. Usually sleep deprived and
hungover
and altered in one way or another.
Yeah.
Anyway, we bring them into the lab and we expose them to a bunch of objects, household objects, cell phones, pencils, combs, and they learn a list of 20 objects. And then they go away for a couple of days and then they come back and we either remind them of that experience or we don't remind them of that experience. That's the crucial reactivation manipulation. And then we expose them to another set of 20 objects, a different set, right? And then they go away and they come back 2 days later and we ask them to remember the first set. And what we showed in these experiments in a variety of different conditions is that if they've been reactivated when they learn the second set of objects, if their memory of the first set has been reactivated, they update that memory with some of the objects from the second list. Even if we are quite explicit in asking them just retrieve the first list that we taught you, but most of the subjects will intrude, will update, and will assume that some of the objects from the second list actually belong to the first list. So they've simply updated their memory based on this reactivation process. And we have shown that this reactivation process is most effectively triggered by bringing them back to the same spatial context in which the initial learning occurred. And this gets back to Todd's example of rats learning about space, because we think that that's crucially implicated in the functions of the hippocampus and the role of the hippocampus in memory. I'll say a bit more about that later.
Yes, we are absolutely going to get to that.
Yeah, but with respect to reconsolidation, given that it has now been shown in emotional memory, in episodic memory, like the learning of a list of things, we now assume that this is a fundamental function of memory, and that the way memory actually works is that it's not so accurate. Memory really is in play all the time, and that every time you do reactivate a memory, the possibility exists to strengthen it, to disrupt it, or to update it so that it is more accurate going forward.
And I think the outcome of that process, whether it is a stronger memory or a weaker memory, it looks like there's no memory at all, depends on a number of factors, including the type of memory it is, and also what the type of interference is that you're using. Like, what is it that you're updating it with? And I think that's where we are now, is trying to understand those different factors in thinking about how we can use our knowledge about the brain systems involved in the malleability of memory to create advantageous uses of memory in the future, either clinical treatments or perhaps improving education.
So just to say, from the molecular point of view, several labs are looking at the notion that what might be happening during reconsolidation is a breakdown of the PKM zeta that's there in the specific synapses that are storing a specific memory, and then those have to be resynthesized. So to get back to your question about how one could combine the potency of ZIP, an inhibitor of PKM zeta, with reconsolidation, would be to try to find agents that will specifically block the new synthesis of PKM zeta, take advantage of basically the degradation that's happening likely when a memory is being retrieved.
And that would be targeted at one memory then?
That would then be the exact way to target a specific memory.
So in theory, you take somebody who has got PTSD, make him or her relive the event, give them ZIP during reconsolidation?
Not ZIP. We don't. So what Liz mentioned was the very first work done with Kareem Nader and Joe Ledoux was with protein synthesis inhibitors.
I see.
Protein synthesis inhibitors inhibit all the synthesis that's happening in neurons. And there are tens of thousands of proteins being made, every few minutes. So, and of all different sorts. So that would be just a disaster. You don't want to do that. But if you could selectively inhibit the synthesis of PKM zeta, that might get to the core mechanism of the memory storage and give you a way of selectively erasing a particular memory.
See, but the,
Not
Is that how it was done in Eternal Sunshine of the Spotless Mind?
all right. See, the trick here is that you want to affect only the synapses
Well, that was done in the
were.
Queens, so we're in Brooklyn. So.
You want to affect only the synapses that were the ones engaged in storing that particular memory.
By the way, you remembered it wrong. It's Manhattan.
So the problem is the problem of specificity. But we know that the brain solves this problem. Because when the brain stores a memory, it stores it in a selective set of synapses. So somehow those synapses are tagged in some special way so that the changes only occur there. So we have to reverse engineer that process. In order to accomplish this selective erasure, we have to reverse engineer that process to figure out and to design the appropriate drugs that will pick out just those synapses that were reactivated during an emotional memory and so on, and affect just those synapses.
How close are we to being able to do this?
Well, I think it's important to point out, I mean, there is one drug right now that has been shown to have this effect in rats with fear memories that we can give to people because it's a very common drug for high blood pressure. It's called propranolol.
Beta blocker.
It's a beta blocker.
Beta
yeah.
blocker.
And we've been having a lot of
People take this to reduce stage fright. Surgeons
Exactly,
take it
yep.
to not have their hands shake while under
Yep.
pressure, et cetera, et cetera.
And that has been shown to be effective in disrupting the reconsolidation of fear memories in rats, and there's been very mixed evidence in humans, so we're trying to figure out, could it work in humans, and if so, under what circumstances. But there is ongoing research. But I think an important point to make is, what we're showing and what Lynn's showing is that understanding these molecular processes doesn't mean we need to use that drug to alter this memory in an adaptive way or in a clinical intervention. It may be the case, given that we understand the timing and the constraints of the molecular mechanisms of reconsolidation, doing something as simple as timing the exposure therapy that you get for PTSD creates a much more effective outcome because we're targeting the reconsolidation process as opposed to creating a new memory that now competes with the old one. So I think these drugs are very exciting that are working in non-human animals, and they give us a lot of information about how this is actually happening in the brain. It doesn't mean that that particular drug is going to be the solution for targeting these things in humans in ways that are going to help individuals, for instance, with PTSD. It may be that that information is going to lead us to new discoveries of easier or safer ways to target these things in humans.
So, having said that, how far are we away from having a drug that might perhaps do that? I mean, are people actively working on this?
Very
we're working on
actively.
propranolol. We're doing some studies on propranolol. But the data is very messy. And one of the things whenever I get a reporter that calls me about reconsolidation and what we're doing, I always try to caution, that I think we're at least a decade away from a treatment of using these mechanisms, even if we're just doing the behavioral interventions, just understanding exactly how they work. So people hear these things and they get very excited, like we're curing PTSD tomorrow, and if I were suffering, I'd want to hear that message too. But I think it's a disservice to people who are truly suffering to not make it very clear, that we're quite a bit a ways from, translating these things. I think what's exciting is, as a memory researcher, it's a hugely exciting time to be a memory researcher. And what is exciting is that it probably will happen, in our lifetime, that we'll figure this out really well, and then for use better or worse.
But there are big hurdles. To getting there, not the least of which are the clinical trials and the ethical issues involved in playing around with drugs that we don't really know what kind of effects they have or side effects they have. So that I think, to emphasize Liz's point, the talking cure, the things that psychologists and psychiatrists do in their offices to help people with anxiety problems are changing the brain in one way or another. They're not magic. Those things also affect brains and affect synapses, and they may be doing it in a way that is more accessible, certainly in the short run, than the kinds of things that are coming out in the animal experiments. Mm-hmm. We may get there, but it's going to be a long time.
Speaking for reporters everywhere, it's less sexy, though.
I'm sure.
What we also want to talk about is the way in which we naturally remember things incorrectly, which is a big specialty of yours. Before I let you talk about it, we do have a video on this topic, a really funny one, so take a look.
So it's my 8th birthday party, a very happy day in the life of little Jonah. And me and my cousin Ben are throwing our birthday party together. We've shared a birthday really since we were little kids. He's a year older than me, but we'd always kind of celebrate it together. And we're having a great time, you know, eating cake, opening presents, and the last thing we do is we're playing piñata. And my cousin Ben, that little bugger, he takes the bat, takes my turn at the piñata, cracks open my piñata, and I am furious. I'm so mad. He's stolen my thunder, and we get in this nasty fight going at it, all because of the piñata. I was really upset about it. And this is a story I've told again and again and again about the day my 8th birthday party was ruined by my own cousin. A couple years ago, I'm talking to my cousin Ben, and I'm saying, do you remember when you ruined my 8th birthday party with, you know, that piñata, and you busted my piñata and broke all the candy? It should have been my turn. Do you remember that? And he looks at me like I've lost my mind. On your 8th birthday party, I was at camp 600 miles north. There is no way I could have ruined your birthday party. And as soon as he told me he wasn't there, I knew it was all made up. I knew I'd invented the story and just told it again and again and again. I had no idea why I invented it. I have no idea where it came from. It was just this fiction that I'd somehow woven into my identity.
I've been accused of doing similar things. So why do we do this? How does something like that happen, and what are the various forms of misremembering? Is that the right way to say it?
Yeah, I think you did pretty well there for a TV reporter.
I knew that was coming. Scientists.
We've already heard from these wonderful scientists on the panel some findings and ideas that suggest that memory is a little more complicated than we might think. It's not as straightforward as we might think. It's certainly not like just bringing up a file on a computer. And examples of memory distortion, or what some of us in psychology call false memory, such as we just saw in the Jonah Lehrer example, are really dramatic illustrations of this point. If when we remembered, all we were doing was kind of shining a light on an image in the brain, well, we couldn't have memories like we just heard, or the experience of memory, because that event had never happened. Now, these kinds of observations provide very important clues for memory researchers, because they tell us that memory is what some of us like to think of as constructive. When we remember an event from our past, yeah, we are drawing on information that we've actually experienced, but sometimes that we're combining that incorrectly with other things that we may not have experienced, or we're mixing up elements of our experience. And these kinds of mistakes can have very important consequences in everyday life, and particularly in the legal system. So let's look at another example that in some ways even more extreme than the video that we just saw. This is an example taken from a memory researcher himself. His name is Donald Thompson. If I could have the Donald Thompson slide. There's a picture of him. He received his PhD in memory research at the University of Toronto, where I got my PhD, working with the same mentor, Endel Tulving, a leading figure in memory research, coined the terms episodic and semantic memory. Donald Thompson then went back to his native Australia and carried on a career there doing research in memory. And all that was going along fine until one day when a stunning event occurred. The police came to his door and informed him that he was accused of brutally raping a woman who had in fact been brutally raped. There was no question about that. And she remembered him so clearly and so specifically that she was actually able to lead the police through her detailed recollection to his door, hence this stunning accusation. Well, fortunately for Thompson, he had an airtight alibi. He could not possibly have committed this rape, because at the moment it was committed, he was giving a live television interview about, of all things, memory and memory distortion. Well, what happened? The woman who was raped was watching that interview when an intruder broke into her house and raped her. And she mixed up her accurate memory of Thompson's face from the TV screen and the rapist. she kind of mixed those two things up. And this in memory research is something we call a misattribution error. We remember some aspect of an experience correctly. She remembered Thompson's face from the TV screen correctly, but we get the source wrong. And misattribution is one of the 7 sins of memory I talk about in the book on the 7 sins. And it's a really interesting one because it shows how when we misarrange elements of our experience that actually occurred, our memory can get us into trouble. This woman had great confidence in her memory. And that's another characteristic of these misattributed memories. People have great confidence in them. They'll swear up and down that the events occurred. And we know that, in fact, from research on DNA exoneration of people who have been wrongfully convicted of crimes, that memory errors of the kind we've just looked at are among the most frequent causes of these wrongful convictions of people who have now been set free who didn't have an airtight alibi the way that Thompson did. I often think, suppose that interview that had been played was taped and he didn't have the alibi, what would have happened? Well, thankfully it was live.
Did they ever catch the actual?
It's a good question. I don't know the answer. You TV reporters do think of some good questions. I don't know.
Maybe the exception that proves the rule, but carry on.
But these mistakes are not just infrequent aberrations. They're things that can happen to us all. And in fact, in the next few minutes now, I'm going to try to induce in you, the audience, the same kind or a similar kind of misattribution memory that occurred in the Donald Thompson case. Okay, so you guys are going to be the subjects now. Maybe we have a few college undergraduates here, but probably not everybody. I hope not. And all you have to do is listen to a list of words that I'm going to say, and I want you to remember these, and I will test your memory for these words in just a couple of minutes, so pay attention. And I'm going to predict right now that in the next couple of minutes, a number of you are going to exhibit a false memory that is kind of like what we just talked about. So here's the word list. Listen carefully. Candy, sour, sugar, bitter, good, taste, tooth, nice, honey, soda, chocolate, heart, cake, eat, pie. Okay? That's it. That's the list. That's all there is to it. Very simple, very straightforward. Now, there are various ways I could test your memory now for that list. I could give you what we call a free recall test. Think of all the words quietly to yourself for a moment that I just said. Try to just retrieve all the words. Think of them for a second. If you can't come up with 10 by now, you have certified brain damage. No, that's not true.
It's not true. It's not true.
Now we're going to do a different kind of test, a recognition test. I'm going to say a word, and if you think it was one of the ones I just said, I want you to raise your hand. And then I'm going to ask you whether you're sure about that memory or not. Okay? The first word is taste. Who remembers me saying taste? Recognize that I said, most people, but not all. How many people are sure that I said the word taste? Maybe about half the audience. Okay, it's pretty good. Taste was on the list. Okay, how about the word point? Does anybody remember me saying the word point? No? Nobody? Boy, you guys are pretty good. Nobody remembers point. Oh. Okay, you're good. Okay, let's go on to the next one. Sweet. How many people remember me saying sweet? Almost everybody does.
Unbelievable.
And keep your hands up. How many people are sure that I said sweet? I did not say sweet. So here we have a situation. I warned you in advance. I was going to try to create a false memory. I told you that you would experience that memory. What did I say? Candy, sour, sugar, bitter, good, taste, tooth, nice, honey, soda, chocolate, heart, cake, eat, pie. Sweet was not on the list, but all those words were related to sweet.
Is that priming?
Sort of.
In a way.
Sort of, except that priming is not conscious, where, as we saw, this is very conscious. Most of the people were sure that sweet was on the list. What you're showing is your memory was kind of accurate, just like the woman in the Thompson case her memory was kind of accurate, but wrong in one critical way. Everything I said had to do with sweets. So your memory for the general gist of what I said was accurate, but the specific memory was wrong. And this is a classic kind of memory misattribution error, where if you get the critical detail wrong, and there's some basis for it in reality, you can have a confident but false memory.
What are the other sins? Should we go through some of those?
I think people are probably feeling scared enough about their own memories now. No. A couple of the other ones are, for example, suggestibility. That's when misleading suggestions and misinformation can lead to these kind of false memories. That's something that's very important in the legal system. Another one I call bias. That has to do with the fact that our memories of our past experiences are kind of colored and skewed by our current beliefs, knowledge, and feelings. So those are the two others that relate to distortion. Another one, several others have to do with different kinds of forgetting. And another one has to do with persisting memories, I call persistence, when emotionally arousing memories are typically very well remembered, but they also can kind of keep us up at night and haunt us. And in extreme cases are associated with post-traumatic stress disorder and other things we've heard about. Liz Phelps has worked a lot on emotion and memory that very much relates to persistence.
So how many people here can recollect where you were on 9/11? Raise your hands. Keep your hands up if you would say that your memories are quite vivid and detailed. If you remember who told you about what happened. If you remember what you were wearing. Not too many. Just thought I'd try. I'm pushing it. How about if you remember what you're doing right beforehand? Most of you? And afterwards? And would you? And if your hand, and these are very strong memories. Only have your hand up if they're strong memories. Okay. So I want to now show you a slide. I'm going to describe a study. This is a very characteristic pattern of memories for a traumatic event like 9/11. And back in the 70s, two researchers, Brown and Kulik, investigated memories for things at that time, like the assassination of John F. Kennedy or Malcolm X. And they brought people in the laboratory and had them recollect these memories. And what they found is they differed than memories of everyday life. These memories tend to be very vivid. You felt like you were reliving the experience when you really thought about it. They were very detailed, and people were highly confident that their memories were correct. So, and they used the word flashbulb memory because they described these memories as if it's a picture taken with a flashbulb. So almost just like you know, they called the print now mechanism. It's burned into your brain what happened on that day. Since the 70s, there's been a lot of research on this notion of what does emotion do to memories that gives them this quality. And surprisingly, what we found is that these memories are not nearly as accurate as you think. So this is just a slide that I used to illustrate a study that was done by David Rubin at Duke University on memories for 9/11, and it's just an example of the kinds of probably 100 of studies that have looked at this issue. And he managed to get people into the laboratory on September 12th, 2001, and he had them write down what they were doing when they heard about the 9/11 attacks, and also some other event that occurred around that time. And it could be, for instance, a study section with friends. And then he brought them back to the laboratory on September 12th, 2002. And he asked them to describe the events in detail. And he also asked them, how confident are you in your memories? How vivid is the memory? You know, are you absolutely sure that this is what occurred? Do you have a sense of reliving the memory when you recollect this? And what he found is that memories for the details of 9/11, not that the event occurred, but for the details of what happened, you know, what you were doing right beforehand, who told you about the event, were no stronger than memories for the details of the study section. These memories declined over time. What was different is you could not convince the participants that their memories for the details of 9/11 were incorrect. So we have, and I'm sure I couldn't convince many of you that your memories for 9/11 are incorrect. I'm convinced my memories for 9/11 are correct as well, all I can say is the data suggests you're wrong. And me too. And the reason, why we think this happens, and can I get this slide on the brain anatomy here? So we looked at the brain systems involved when you're retrieving memories from 9/11 versus other life events that occurred around that time. And what I've plotted here in the brain are some of the structures we've talked about. So in red, you see the amygdala. In yellow, you see the hippocampus. It's a sort of long structure. It's named for a seahorse. And underneath it, you see a region called the parahippocampus, which is also involved in aspects of memory. And what we know emotion does, and when you encounter an emotional event, the amygdala responds. The amygdala has an influence on all the stages of memory encoding. So, of all the stages of memory, I should say. Your attention changes, right? So you focus on the emotional event. You have very good perceptual experiences for the event for the emotional thing that's in the environment, but you can't look away. So you also have worse memory. You encode the details of other things worse. The classic example of this emotion capturing attention is if you're driving down the highway and you're in a traffic jam. What you find is, if you get to the place where the traffic jam started, sometimes you get annoyed because you realize the reason there's a traffic jam is not because your lanes of the highway are blocked, but there's an accident on the other side of the road that everyone's slowing down to look at. So if you get annoyed, but then of course you have to also slow down and look at the accident on the other side of the road. So emotion captures our attention. We have to pay attention to it. We get better memories for those few details, but we're ignoring other things like driving at a reasonable speed. And the amygdala plays a role in that. The amygdala also plays a role in the storage of memory. So you've heard about this consolidation process. So the amygdala modulates the consolidation of hippocampal-dependent memories of your episodic memories for what occurred. So now you have a little bit of information coming in about the emotional event itself, but what came in got stored very strongly, but you didn't actually store a lot of the details of memory because you were so focused on the highly emotional event. And then when you retrieve it, the consequence is having these very strong memories for a few details makes you feel very confident in your memory. It gives you a lot of vividness to your memory. But the truth is, your confidence then spills over to other details that you didn't encode well. And we know this from looking at the brain because what we see when we ask people to retrieve memories from 9/11 versus other life events is we see increased activation in the amygdala when they're retrieving the 9/11 memories and they're asked to encode the details of those memories and think about them. But we see less activation in this region called the parahippocampus, which is in blue, and we know that region is important in memories for a lot of details. So the brain signals are consistent with the idea that what you actually have with 9/11 and other traumatic events is very strong memories for a few details that give it the memory this vividness, but actually very poor memories for a lot of the details that occurred. And then you might ask the question, why would that happen? Why would we have a memory system that makes us really believe a memory is right when some pieces of it, not all of it, but some peripheral pieces of it are wrong? And then this gets us to sort of what the function of memory is. So memory, one of the primary functions of memory is to be able to use our experiences of the past to be able to act adaptively in the future. When you're not sure about your memory, the confidence you have in a memory is a signal to you that, if you're not very confident, you may not act on that memory until you get more information. If you're highly confident about a memory, you don't need more information, you don't need to look for anything else before you know how to act. And so it may be that this sort of increased confidence we have for highly emotional memories is so that when something comes up that reminds us of something that was dangerous in the past, we will act quickly. We don't have to be unsure about our memories. We know that there's some danger there, we should move forward, and probably the little details, like what you were doing right beforehand, don't matter so much. So we think that you have this enhanced sense of vividness and recollection for highly emotional events that's disproportionate with the accuracy of your memory, so that you can use that, so that when something's highly emotional, you're very likely to pay attention to use that information to act quickly in the future.
I'm going to attempt a segue here, given that I have pretty much zero understanding of the brain. Let's see if this works. So obviously, the amygdala plays a big role in how we remember, but apparently we also have, there's also a huge role for the hippocampus, which is spatial, amygdala being more emotional. Am I right thus far?
Sure.
Okay,
Yeah.
that's all I have.
Yeah.
So and we want to talk about the role of the hippocampus, which is truly fascinating. You might have heard about this recent best-selling book called Moonwalking with Einstein, which talks about people who are specialists in remembering stuff, memory champs they're called. It was written by Joshua Foer, who couldn't be here tonight, but he did tape something for us, which I want to show you, and then we're going to get into the hippocampus. Check it out.
The kind folks at the World Science Festival have very generously given me a list of 150 random words that they want me to memorize. And I'm going to do that by using an ancient technique that was invented in the 5th century BC called the memory palace. And the idea is I'm going to create wild, crazy images of the words on this list and tie them to a space in my mind. So the first word on the list is science. So I'm going to imagine right here Albert Einstein sitting on my shoulders and slapping my cheeks. That should be totally memorable. The second word on the list is heart. So I'm actually going to imagine a gigantic beating bloody heart, and I'm going to just impale it on this sundial. I don't think I'm going to forget that. All right, so the third word on the list is speech. So I think I'm going to imagine Colin Firth from The King's Speech stuttering right here. That'll be memorable. The next word on the list is green pepper. So I'm going to see a rotting, stinking green pepper right here in this bush. Error, university, t-shirt, violence, chicken, nation, football, photo. The final word, which is tool. At this bamboo fence, I'm going to see a gigantic monkey wrench just embedded in the fence. Whew, that's it. All right, now that I've remembered all these words, I'm going to go distract myself for a few minutes and then come back and see if I can still remember the list. 3.14159. Wilson, Harding, 6535. That's as far as I can go. So it's recall time. Let's see. The first word was science, then heart, speech, error, university, t-shirt, violence, cry, children, mathematician, legend, television, fear, day, famous, gorgeous, convent, sky, match, color president, robo, dream, penny, holiday instinct, real website, newspaper, a car, unspeakable, crack, asylum, hat, challenge, housewife, family, toaster, age, officer, eggs, football, photo, tool.
Len, explain that to us.
Sure. So he made a reference to the fact that this had been invented or discovered in the 5th century BC. So the actual story goes like this, and I think we have enough time for me to go a little bit off script.
We can cheat.
Simonides, who is the Greek person who discovered this, was at a party in a big building and was called out. And when he was called out, the entire building collapsed and everybody was demolished. And the survivors were interested in identifying who was the remains, so to speak. And he reconstructed who was sitting where by remembering where they were sitting. And it was on the basis of his doing that he understood that remembering things on the basis of spatial location works pretty well. So he then invented this method called the method of loci as a memory tool. And this method was then picked up in the Middle Ages by rhetoricians and by individuals who had to have good memories. And they created memory palaces of the sort that Joshua just described. And they used this as a way of remembering sequences of things, speeches they had to give, oral narratives, and all those things. And at that time, nobody really understood, why did this work so well? But what came in this century, we had the work that Dan referred to with this patient HM, who had damage to the hippocampus that caused big memory deficits. And then about 10 or 15 years later, a fellow named John O'Keefe, who I worked with, discovered that in the rat hippocampus, the individual neurons, some of which Todd was showing you, that those neurons respond most effectively to where the animal is located in space. So that in the rat, it appeared that the hippocampus was interested in space. And then there was a big problem for the field. How do you put those two together? So why is it the case that a brain system that is so important for memory is also so important for space? And so the answer, if there is an answer yet, and actually this is still somewhat unclear, the answer is that we probably use this kind of spatial framework as a way of remembering the episodes of our life. They all happen in a particular location. That's why the spatial context was so important in the experiments we did on the reconsolidation that I described before, so that there is some very deep connection between the way we remember things and the spaces in which those things occur. And we use a spatial scaffold, as it were, to help us remember the events of our life.
In Josh's book, he sort of posits that we evolved this way because we had to remember the way to the clearing where we killed the mastodon.
No, absolutely. I mean, so our ability to sort of, there's a lot of interesting connections here. First of all, being lost in space is a profoundly terrifying thing. We all really want to know where we are. If you come out of the subway and you suddenly don't know where you are, it's a very anxiety-provoking. So knowing where you are in space is pretty important, precisely because if you don't know where you are, you may be in danger. So knowing how to get to the safest place, knowing how to get to food, knowing how to find water, knowing where your mate might be, and so on, all those things are evolutionarily extremely important. And the circuits that are crucial for this kind of spatial knowledge that are linked with memory go way back in evolution. I mean, you can trace them back 300-400 million years. So this kind of ability, the need to know how to get around in space and how to find your way in space is fundamental for any moving organism. So we'll leave plants out of the equation for the moment. But for animals, it's an absolutely crucial ability. And it somehow got integrated into or became a basis for our ability to remember the episodes of our life in a way that turns out to be very effective. And so memory tricksters use it, but it's not a trick. It's actually the way the mind and the brain seem to work.
I mean, as Josh shows in his book, I mean, memory champs build these extraordinary palaces.
Right.
Huge.
Right.
It'd be very expensive by New York real estate.
You would think so. Can also be very dangerous. One of the people who did this in the Middle Ages, Giordano Bruno, who was a famous philosopher, was actually burned at the stake for using these kinds of methods because they thought he was, engaging in some kind of deviltry. So I think things are a little bit easier. If you get the wrong idea in science now, you don't necessarily get burned at the stake, but bad things can still happen. But
mostly other scientists being mean to you.
Precisely. Luckily, we're all friends. But the other connection here is that this system that is so crucial for remembering, sort of navigating through your past and navigating in the world spatially in the present, also seems to be crucial for navigating into the future. And I think Dan could probably say something about that connection as well.
Yeah, that might be a nice point to finish up on, because it also connects back to the issue of memory distortion and the question of why is it that we have the memory system that seems to get us into trouble? Why do we mix up elements of our past experience? And one idea that we've been working with lately is the idea that this might be a consequence of the fact that we critically use our memories to project ourselves into the future, to plan for upcoming events on the basis of our past experience. And we need a memory system that allows us a lot of flexibility in order to do that. In other words, a system that allows you to kind of rearrange parts of your past to think about upcoming future events, to project ahead to, well, how is this conversation with this person going to play out? And drawing on my past to use it to think about imaginary scenarios in the future is a very important function of memory. And so maybe a system that's set up to be flexible that way is also going to leave us prone to some of the errors that we've discussed. And indeed, what we have found, if we have that slide on future comparison, is that many of the same brain regions shown here including the medial temporal lobe, and that's the part of the brain that includes the hippocampus. It's right in there in the medial temporal lobe. When we put people in a brain scanner and we ask them to remember experiences from their past, these regions light up, this network that includes the medial temporal lobe, some regions in the middle of the brain that are shown here as the precuneus and retrosplenial cortex in the back, the medial prefrontal in the front. All these regions come online when we remember things that actually happen. What's interesting is that if we just imagine things that might happen to us in the future, these same structures come online pretty much in the same way. And a number of labs have shown this kind of effect. So these kinds of findings give credence to the idea that there's a lot of overlap between remembering the past and imagining the future. For example, some of the amnesic patients we've been discussing who have terrible problems remembering their past, well, many of them also have problems imagining their future. So this provides a link between kind of the past and the future, and we think that might help to understand how memory is related to spatial navigation, because these regions come online, and also some of the reasons why we make some of these memory errors.
Are some of these people, interestingly, happier because they're forced into the present moment?
That's a good question, but I'm not a social psychologist, so I don't know if I can answer that one. No, I think some of them probably are happier than they would be otherwise if they would be constantly reminded of the problems that they're having remembering their past. It relates back to the awareness question that you raised in the beginning.
But so many of us spend so much of our time ruminating or projecting as opposed to.
That's right. If you don't have that capacity, you might be freed from, for example, the sin of persistence that we talked about. Persisting memories wouldn't persist. And the flip side of that into the future is basically anxiety and worrying about upcoming events. So perhaps there is some gain there.
But HM, the patient that Dan referred to at the beginning, actually reported that he didn't report it being a happy state. He reported that he felt like he was constantly waking from a dream, and he didn't know what had just happened. He didn't know what was going to happen. So you didn't get the feeling that this being in the moment all the time without a past and a future was a particularly happy thing.
The message is everything's overrated. Or are you threatening me?
We could try. No, we could try.
He's got some zip for you.
Some zip in his pocket.
Thankfully, you are restrained by your professional ethics. So now's a good time to wrap up. Lynn, Elizabeth, Todd, and Daniel. Did I get that right?
You did.
Built a little palace for you guys. Thank you very much. You were a great panel. I learned a ton. And thank you, everybody, for coming.